Welcome to chapter 6, and we're going to be doing infinite series now. I really like this chapter. I think you're going to really like it. In some ways, this chapter is going to take us back to calculus. I guess whether or not you like it may depend upon what you thought of calculus when you did it. The good news is that this is one of the sections that showed up in your calculus sequence that you already had kind of the level of maturity that you were talking about some of these proofs and some of these tests as well. So what we're going to do is we're going to go through like all the tests that we had in calculus class. We're going to talk about why they're true, and the same reason that they were true in calculus class is true now. The only difference is we've got a little better language to talk about it, and so we're going to couch it in terms of epsilons and deltas and things like that. But you might remember that an infinite series is just some series that we write like this. It's just the series as k goes from 1 to infinity of our series. And really, we're always asking a question. We're asking, does it converge or does it diverge? And this is the question over and over and over again. And for the mathematician, we're a lot less interested on what it converges to, although we will talk about that in the last video that I make for this series. We're usually just a lot more interested in if it converges, because if it converges, we can approximate it. But the last video will be really good. I think it'll be quite interesting. Okay. All right, so let's start by talking about how do we approach these things. And the way we approach them is by connecting infinite series back to sequences. And the way we do that is the partial sum. And so we call the partial sum of a series Sn, and Sn is just the sum where we stop at the letter n of a sub k. And notice because this is a finite sum, this is just some finite number. Right. So whatever our sum is, maybe I should put a colon here. So whatever this finite sum is a finite number. And what we're going to say is we're going to think about the sum k from 1 to infinity of a sub k. And so we're going to talk about this converging. And what we're going to do is we're going to basically equate that converging to the idea of this partial sums, which creates a sequence converging. And what's good about this is now everything that we know about sequences we can use for series. The only difference is instead of talking about the values that go in the series, we're talking about the sum of the values. But we created our own sequence, and so we know all sorts of things about the sequence. So for example, so let's start with some key examples and kind of think about the partial sums here for each one. So the first one we'll do is 1 over 2 to the n. And what is this series? This series is 1/2 plus 1/4 plus 1/8 plus 1/16 plus. And you can see that this is going to keep going on and on and on and on. But let's ask, what are our partial sums? Well, the first partial sum is just 1/2. Our second partial sum is the partial sum 1/2 plus 1/4, and it looks like we get 3/4. Our third partial sum is 1/2 plus 1/4 plus 1/8, and this ends up being 7/8. Our fourth partial sum is 15/16, on and on and on and on. And we'll talk a little bit in just a moment. We will give this a name that we already know, and this is called a geometric series. And when we talk about this as a geometric series, we will talk in general about why these converge and what they converge to. But for now, let's just make the quick observation that these partial sums are always equal to 2 to the n minus 1 divided by 2 to the n. And well, this sequence converges, so we know that this converges to 1. Now what does that mean? That means that our series, k goes from 1 to infinity of 1 over 2 to the n, must converge to 1. So let's just put equals. We'll say equals 1. And when it converges, we'll just put an equal sign here. By the way, as we talk about these sequences converging or diverging, we'll include infinity on this. So if the partial sums converge to infinity, then we'll say the series converges to infinity as well. Usually we consider that diverging, because usually we're not interested in the series going to infinity, but there are times where maybe we are. Okay, so this is great. As I said, we'll get a little bit more detail, and this is just kind of introducing us to thinking about series. All right, so let's go to our second example, which is the example of -1 to the n. And let's think, what is this series? This series is -1, 1, negative 1, 1, negative 1, 1, and it keeps going forever. Oh, wait, I should have put plus signs inside of here. That was a bit of a fail on my part. So let's write it again. So negative 1 plus 1 plus negative 1 plus 1 plus negative 1. Okay, so let's think. So what are our partial sums here? Well, our first partial sum is just whatever that first term is, and it's negative 1. Our second partial sum is what happens when we add a 1 to it, and we get 0. And our third partial sum, well, now we're, our third partial sum, well, now we're back to here, is back to negative 1, and S4 is 0. And maybe we see a pattern with these. And the pattern that we get with these is that Sn is, let's just write it like this. Sn is negative 1 if n is odd. And it's 0 if n is even. I guess we could have written this with a negative 1 to the n notation as well. But let's just write it in this bracket. But you can quickly see that this does not converge. So this definitely diverges. This is an example we did a bunch when we talked about sequences. So this sequence, the sum of negative 1 to the n, this is a divergent sequence. So this one diverges. It does not eventually gather towards anything. And this is an interesting one because we can see that it diverges, but the values of the sequence the values of the series don't grow infinitely large. They're just always bouncing back and forth between positive infinity and negative, or positive 1 and negative 1. Okay, now to the last one, which is the most interesting example that we do. And this one has a name. This is called the harmonic series. And you probably remember this from your series. This is kind of like the key example that changes or influences the way that we think about series. But what is the idea? This series is of 1 over n is the series of 1 plus 1/2 plus a third plus a fourth plus a fifth plus a sixth plus, I'm going to keep going a little bit, plus an eighth, plus, okay, and we keep going like this. And the question is, well, what does this do? Well, we have to think about our partial sums, but there's a trick to thinking about it. And so I'm going to just show us the trick. The trick is to only look at the powers of 2, every, power of 2 partial sums. So S1 is just 1, right? S2 is 1 plus a half. And now let's ask ourselves, what is S4 going to be? Well, it turns out S4, if I come here and look, that is these 4. But what I'm going to do is I'm going to try to group these 2 together in a clever way. And so S4 is 1 plus a half plus a third plus a fourth. But what I want you to notice is that this third is bigger than a fourth, right? So this term right here is bigger than a fourth. So I can say that this series, whatever it is, must be bigger than 1 plus a half plus a fourth plus a fourth. But that means that S4 is bigger than 1 plus a half plus a half. All right, let's try this again. And now let's do the same thing for S5. Or not S5, S8. So S8 is 1 plus a half plus, and then I'm going to group my 1/3 and my 1/4 again. And now I'm going to group all the rest of these, 1/5, 1/6, 1/7, and 1/8. And what I'll notice is just like this first term is bigger than a fourth plus a fourth, all of these terms over here are bigger than my 1/8 term. So this must be bigger than an eighth plus an eighth plus an eighth plus an eighth. But what you notice is my 2/4 come out to be a half. And so my S8 is bigger than 1 plus a half plus another half plus, and now this is 4/8, so this is also a half. And what you see I've done is I found one series bigger than 1, I've found a bigger series bigger than a 1 plus a half. I found a series bigger than 1 plus a half plus a half. And then I found a series bigger than 1 plus a half plus a half plus a half. And what you can see is that this trend is going to keep going on and on and on. So I'm going to try to write a formula for it. And so my formula is basically going to say this. Let's leave that last one so we can look at it. And our formula is just going to say that our nth partial sum is bigger than or equal to 1 plus, oh, not the nth partial sum. Let's call it the 2 to the n partial sum is greater than or equal to 1 plus, and how many halves do we get? Well, 8 is 2 to the third. 4 was 2 squared, so we'll just go n divided by 2. So our 2 to the n partial sum is bigger than that. So by the time you get to 1,028, that's bigger. 1,028. I should have done this beforehand. I think that's 7. So that's bigger than 1 plus 7 over 2. Yeah. Okay. So it turns out that these can be made as large as possible. So this tells us that our sequences Sn diverge to infinity. So what does that mean about our harmonic series? Our harmonic series diverges. And this is our first really interesting one. And what makes it interesting is that it feels, when you just look at these numbers, it feels like it converges. And we've seen all along, 1 over n always tends to converge whenever we think of it as a sequence. Well, that's not true when you think of it as a series, because when we group it just the way, we see that this series keeps growing larger and larger and larger. And so, the sum of 1 over n can be made as large as we like, even though these terms can be made as small as we like, right? So eventually, we're adding 1 billionth plus 1 billionth and 1 plus 1 billionth and 2. So those are super ridiculously tiny numbers, but if you add them together in large enough chunks, they still give you a value bigger than a half. So you eventually grow larger and larger and larger in these things. So this series diverges even though the individual terms become really, really large. And this kind of messes with our brain a little bit, but it's kind of one of the big ideas for thinking about series. And so this brings us to kind of the first, brings us to the first set of theorems that we're going to talk about. And the first set of theorems says, well, we can notice that things that are true for sequences must also be true for series. And the first one, the one that we're going to use a lot, is called the Cauchy criterion. But if you look closely at this, you just say that this sum converges if and only if for all epsilon there exists a capital N such that when n and m are greater than n, then that sum, I messed this sum up over here. The sum from n to m is greater than k. That was a copy and paste error. I should have been a little bit more careful. Okay, so the Cauchy criterion says if we go from n to n, and let's just assume over here that n is less than m. It doesn't matter which one's the bigger one. Then the Cauchy criterion says we can do that. Well, why is this? Let's not go through all the gory details, but let's just quickly notice that this converges if the sequence Sn converges. But what is this term over here? Well, this term right here is just the term, the Sm minus Sn, and we're taking the value, the absolute values of it, and we're saying it's less than epsilon. So what are we really saying? Well, we're saying that this sequence, Sn converges if the sequence is Cauchy. So what we're really saying is that Sn converges if and only if Sn is Cauchy. So and that's why we call it the Cauchy criterion. As you see that we've basically translated this sequence being Cauchy into the language of a series being Cauchy. And so we don't have to do any more work at this point because we proved that when sequences converge when they're Cauchy. So this is kind of a general method of how we approach a lot of these proofs is we start with a series and then transition to the sequence and use what we know about sequences to prove our theorems to be true. Okay, so on top of this, we have a bunch of other theorems that should also hold true. whenever we go through. So one of those theorems is just the definition of convergence. So it's that a k goes from 1 to infinity of a n converges. Well, it's just, well, that means that there exists some capital N such that if n is greater than capital N, the sum as n goes from 1 to n of a sub k is less than epsilon. And this is just our definition for sequences, right? So the sequence converges if there exists a capital N such that for all n greater than n, the sum of the series is that is less than epsilon. Okay, so sorry, not that is less than epsilon. So this converges to L if that is minus L is less than epsilon. Sorry, I was messing my whole thing up. But we can also like do a similar thing, which if we take the L's out, we can say that the sum from n to infinity should be less. The sum as k goes from n to infinity of a sub k should be less than epsilon, and that comes from the Cauchy criterion that we had a second ago. So there are a few things. We can look at the tail and show that it has to be less than epsilon. We can look at we can use this Cauchy criterion. We can use the definition of series. Two more that kind of make complete sense is the fact that the sum of AK plus BK should equal the sum of the AKs plus the sum of the BKs. This is assuming that AK, the sum of AK and the sum of BK converge. Sorry for my handwriting. So if they converge, then we should see this sum should work out. And why is that? Well, because we know that if you have an infinite number of, you have a finite sum, if you have the sum as k goes from 1 to n of AK plus BK, we know we can split a finite number up. And so therefore, our partial sum, k goes from 1 to n of AK plus the sum as k goes from 1 to n of bk. And why can we split these up? Well, this is just the way addition works, right? We know addition is associative, so I just reassociate all my ak's together and all my bk's together. But you'll notice over here, this is that Sn for those two, and this is some like I'll call it S. Let's put a little prime in, and then this is a second S. Double prime event. So these primes are not connected to derivatives. I'm just trying to say that this sequence of partial sums is equal to the two sequences of partial sums. Both of these converge, so therefore this sequence should converge. So all I've done is translated it from series to sequences, and we know that sequences work in this summative way. Now, this doesn't work for addition, for multiplication. So if I were to try to put a multiply sign here and put a multiply sign here, that fails. And the reason why it fails is we can't simply factor a bunch of things multiplied together in this way, right? So if you have A1 times A2 times B1 plus A2 times B2, this is not the same as A1 plus A2 times B1 plus B2. This is not the way that factoring works, right? So you'd have to add some intermediate terms in there and do some fancy factoring. And so multiplication does not work in general because this factoring, we've seen that it works really well if you have only two things. But notice we're not talking about infinite series, and so this is going to explode and not work out. So therefore, we can't connect the series on the left with the sequence on the left with the sequence on the right. But one that does work is if you have some sort of constant in here, and the book likes to use alphas. So I'll do alpha a sub k. This is alpha times the sum as k goes from 1 to n of a sub k. And this is just because if you have a sum of n things, you can factor them out. Okay, so some of these series work and some of the series don't work, and so this tells us that the series from as k goes from 1 to infinity of alpha ak is alpha times ak. So that actually works, assuming that series series works. So you can take out constants, you can split up addition, as long as you know your series converge. If your series don't converge, we'll see that we're not allowed to do these tricks anymore, and that's going to mess us up. However, multiplication we're not allowed to do. We're going to have to be a lot more careful, and that's something we're going to talk about in the second video, how to approach things with multiplication. Okay, but what's the big picture here? The big picture is as we go through proofs, and as you go through your own proofs, you're going to want to constantly take the series and back it back to the partial sums, because that's a sequence, and then use all the things we know about a sequence to start attacking the problem. Okay, let's just talk about the divergence test. The divergence test is pretty similar. It's pretty simple. It says if this series exists, AK as k goes from 1 to infinity converges, then that means that the sequence itself must converge to 0. If it converges to anything else, then it's going to fail, and if it diverges, then it's going to fail. So that sequence must converge to 0, and I think you can see a lot of reasons why. One thing that you could do is you can go, well, if by the way, this makes complete sense, right? Because if it doesn't converge to 0, then this ends up being bigger than some L value, but then your series at the end ends up being plus L, plus L, plus L, plus L, dot, dot, dot. And so what you could see is that if this thing converges, or maybe you have if it converges to some L, maybe you divide these by 2 to make sure that you're always getting some positive, some positive amount. And that's obviously going to diverge. So what if I don't sketch the proof and I can just kind of tell you how it works, right? So that's the big idea of the proof here. Okay, but the way this is often used is backwards. You often use the converse theorem, which says that if that sequence does not converge to 0, then the sum diverges. Right, diverges. Then it doesn't converge to any finite number. Okay, so if that series does not converge to 0, then if the sequence doesn't converge to 0, then the series can't diverge. And this is a great test because if you're given some series and you're not sure about it, it's like the sum of n plus 1 over let's do n minus 1 over n plus 1, you're like, that's an interesting series. What's going to happen here? Well, the answer is this problem is really simple because we know n minus 1 over n plus 1 converges to 1, so that means this thing has to diverge because this number doesn't go to 0. Now, however, what we saw earlier with the harmonic series says that the opposite of this theorem is false. So let me write down my false theorem and just say, notice 1 over n does converge to 0, but that sum still diverges. So the way I talk to calculus students about this is we kind of have this hierarchy, and usually the divergence test is one of the first things that you think about. You look at the series and go, oh, is it converging to 0? If the answer is yes, then you get to keep moving on with your problem, and if it's not, then you're all done with your problem. So often I kind of have this decision tree, and you kind of have an converge to 0. If you get the answer is no, then you know diverge is the answer. If the answer is yes, then it could be either one. You basically keep going, and you try other tests. Okay, so this is a real temptation for calculus students. I hope you all aren't tempted by this, but it's real tempting to say, oh, the terms go to 0, so the sequence must converge, and that's absolutely not the truth. Okay, let's talk now a little bit about geometric series and what is a geometric series. A geometric series is just a series of the form x to the n, as n goes from 1 to infinity. So, for example, that very first one we saw was that very first series we saw was 1/2 to the n, and that one converged to 1. Right, so geometric series is just some series that's of this term. Okay, so and by the way, we usually start at 0 instead of starting at 1 for these. But at any rate, it turns out that if you have a geometric series, and let's start at 0 because that'll be a little bit nicer. And that should be one point I made way back here. Whenever we did our series, we kind of assume that we always start at 1, but you can start at any number you want as long as you're not getting undefined terms somewhere along there. And all the theorems hold true no matter where your particular starting point is. But okay, so let's ask, when does this thing converge? And the answer is, well, what's our partial sum? Our partial sum of this is x of 0 is 1 plus x squared plus ... plus x to the n. Okay, so that's our partial sum. And now I'm going to do a bit of a trick. So this is a trick in mathematics. This is a finite number, so I can easily multiply both sides by Sn. And I'll get x plus x squared plus xn plus xn plus 1. And now what I can do is just subtract them. Again, these are finite numbers. They're a finite number of things. I can subtract them just fine. So Sn minus x times Sn equals, well, now when I subtract, I get every term canceling out except that first one. And so you'll notice this x cancels with this x squared cancels, and everything cancels except that first and that last one. And so I get 1 minus x to the n plus 1. So that means 1 minus x times Sn equals 1 minus x to the n plus 1. And so what is my series? My series is 1 minus x to the n plus 1 divided by 1 minus x. Now, let's ask some questions about this series. First, I need to notice a few things. Well, what happens if x equals 1? If x equals 1, then we're dividing by 0, and so this is a little problematic. However, we'll see that's gonna fail our term. So, but let's just ask a real question. We'll ask, what is that limit? So let's just assume x is not 1 and see what's going on. So if x is not 1, then we really have two cases. We have the case where the absolute value of x is bigger than 1, and we have the case where the absolute value of x is less than 1. So if the absolute value of x is greater than 1, then 1 minus x to the n plus 1 over 1 minus x, that goes to infinity or negative infinity, but that diverges, right? You know, suppose x is 2, then what you see is you get these, and the reason is because this value right here is consistently growing larger and larger and larger. Okay, so that is definitely not a convergent sequence. However, if absolute value of x is less than 1, then x to the n plus 1 is going to be converging to 0. So what happens to that sequence? So that sequence is converging to 1 over 1 minus x. And this ends up being a really nice result. Okay, I didn't go through all the details, so the textbook might say a little bit more than this, but I think this is kind of at the heart of what's going on. And by the way, what if x is equal to 1? Then we're dealing with the sum as n goes from 0 to infinity of 1, but that obviously diverges. By the way, you can also see that it must diverge if x is bigger than 1 because it fails the divergence test, because these things don't converge to 0. Okay, so let's go this out and just write out the geometric series test in all its glory. And so what it says is that this sum, the sum as k goes from 0 to infinity of x to the k, converges if and only if the absolute value of x is less than 1, and more than that, this is one of the few times we actually know what the sum is. The sum of x to the k equals 1 over 1 minus x. So for that example that we did earlier, our x value was a half, and so we got 1 over 1 minus a half would equal 2. Oh, why is it off by 1? It's off by 1 because we started at, 0. It's off by 1 because we started at 0 instead of 1. So when I did the problem earlier, I started at 1. So I'd have left off that very first term, which was equal to 1, which makes it 1 bigger. Okay, but at any rate, that sum equals a half. Okay, if you read the book, it's a little bit more careful. It says, well, this is true no matter where we start, so it starts it at an n instead. But this formula is again only true if x equals 0. Okay, I think we can just do the x equals 0 term and then just recognize what's going on when we're bigger than 0. But the geometric series is really important because we know exactly when it converges, and we also know exactly what it converges to, and so it's a really important series in the world of mathematics. Okay, let's shift forward a little bit, and what we're going to do for the next few proofs is we're always going to assume that a sub k is positive, and a sub k being positive gives us a few really important results. One important result is, let's see, did I make myself a slide for this? No, I didn't. Okay, good. So one important result is just noticing something that's true about these a sub k's. And it's just that if the a sub k's are positive, then what does be true about our partial sums? Then our partial sums must be an increasing sequence. Let's put a little sequence sign. Must be an increasing sequence. Why must it be increasing? Well, if you're only adding positive numbers to it, then your values are only getting larger, right? Because Sn plus 1 is Sn plus a positive amount. So Sn plus 1 must be bigger than Sn. So Sn is a increasing sequence. And if, in fact, it's strictly increasing as long as we say positive. If we say greater than or equal to 0, then it's increasing in the sense that it's non-decreasing. Okay, but Sn must be an increasing sequence. So what we know is we know that if it has an upper bound, so we know that if that Sn is bounded above, well, we have the monotone convergence theorem. The monotone convergence theorem says if it's bounded above and increasing, then it must converge. And so this is a really nice way sometimes to show that things converge, is once you know that every term is positive, you don't have to know what it converges to, you just have to show that it's bounded above. And once you show it's bounded above, then you know it must converge to something by the monotone convergence theorem. It turns out that the other is also true, right? It turns out that if it converges, it has to be bounded above. Well, that's just the definition of convergence, right? If it's not bounded above, then that means it's going towards infinity and not converging. Okay, but this is a nice result for us. Okay, let's move now to the three really big tests that work whenever our sequences are greater than 0. And here we're going to call our sequence a function because we're going to try to compare it to a continuous function, the function f of x. And so remember here that f of k is going to have two properties. It's going to always be positive, and our f of k is going to be a decreasing function on that interval 1 to infinity. Now, at the heart of the integral test is something that you saw way back in calculus class, but it's a way to visualize these sequences that's going to connect it to our integrals. So let's visualize a sequence. One way of thinking about a sequence is to think of it like this, and that is we're going to have 1, 2, 3, 4, 5. So one way of thinking about a sequence is you take whatever your A1 term is, and we'll put it right here on our graph, and then we could just draw like a box at the height of A1. And what is the area of this box? This box has an area of 1, which is the width, times A1, which is the height. So this area is equal to A1. And then similarly, if A2 is somewhere here on the graph, we can draw a box representing that one. A3, we can draw a box related to that. A4 and A5, and we'll have two more boxes that look like that. And we can keep going on and on and on as we draw these things. Well, this gives us a nice connection to our integral. And so what you notice is that if I were to draw an integral on here, what would the integral look like? Well, it would go through all of these points because the f of x and the f of k are equal at the integer values, but because it's decreasing, our integral would be going downward And our integral would look something like this. And so our integral from 1 to infinity is actually calculating that area right here. And we can see right now what is the difference between the integral and the area. Well, we can see right now that this integral from 1 to infinity of f of x dx must be strictly less than that sum as k goes from 1 to infinity of f of k. Now this tells us something nice, because that means if this integral goes towards infinity, if it diverges, then what does that mean? That means this one also has to diverge. So we see that the integral diverging means your series has to diverge, because your series is always bigger than your integral. And if your integral is growing infinitely large, then your series is also growing infinitely large. We should be more careful about this if we want to actually write a proof out. What sort of proof would we write? Well, our proof would look something like this. We would end up taking each of these sequences and think about the partition that is made up of k and k plus 1. And then we would do this from, instead of going from 1 to infinity, we would go from 1 to n, and the sum from 1 to n. And we'd think of those partitions, k and k plus 1, and then we would compare the value of the series. So S of n is just the sum of f of k times 1. But then if I compared my integral is my integral from 1 to n of f of x. Well, this is going to be somehow related to that upper and that lower sum over the course of the region. So this is related to the upper sum, which is u of f on that partition. And notice that our u of f on that partition is, let's do the lower sum. So then if I do my lower sum, then this integral is always going to be bigger than that lower sum. But notice my lower sum is smaller than my SNs. And then I can say, well, that lower sum is smaller than my SNs, but that lower sum has to be larger than any m. So then I take like some arbitrary capital M value, and then this is larger than some capital M value, but then that would imply that my Sn is also larger than that capital N value. So I see that my series can be made arbitrarily large, so it's also large by thinking about the lower sums. Okay, well, what would I do if they converge? Well, notice if they converge, I get the exact same story, except now I'm thinking about the integral in terms of my upper sums, and I can do the same exact story but with upper sums and get that this integral is less than upper sums. I can just turn everything around here and say that this is less than the upper sums here, and my upper sums have to be always bigger than or equal to my SNs, but those upper sums now are less than epsilon, or some L plus epsilon. So my SNs also have to be less than the L plus epsilon. So I've bounded them, and they converge and things like that. Okay. So again, I'm not writing out all the details, in part because I'm lazy, and you've kind of got the book you can look at and look your way through, but this is at the heart of why it's true. And the heart of why this integral test is true is because we can compare these sums over this partition where we just split up each one to the series values over those partitions. And it ends up being a really nice result. And so the final result is just that this series converges only when the integral converges. Now, in truth, we don't use this very often, because most of the time taking an integral is a little painful and tedious, and there's usually a better test to use. But there are occasions when this makes a lot of sense. Maybe one where you're doing like a U substitution or something, or something like you're trying to do, say, the series of e to the negative k as k goes from 1 to infinity. Well, this is actually going to be quite hard. Well, I guess this one isn't so bad because this is just geometric. This is just e to the negative 1 to the k power, and that's e to the negative 1 is less than 1. Okay, so I guess that was not a good example. But maybe something with an e to the x or something like that, or a natural log. It's not so obvious how to make comparisons here. If you can take the integral of it then the answer works really well. Okay, so, oh, by the way, what's a good one? Maybe k e to the negative k. You could use like a integration by parts or something to do x e to the negative x to solve that problem. And this one's like not at all obvious what's going on. Okay, great. I'm glad that we were able to talk about that. So the p-series is the first example of when is really an example of when we use the integral test. In some ways, it's maybe the most useful example of the integral test. And a p-series is just a sum that looks like this, 1 over k to the p power, as k goes from 1 to infinity. Okay, so what we're going to do is we are going to compare this, just like we did a second ago, to the integral from 1 to infinity of x to the p dx. Now, one thing we know about this, x to the negative p dx, because we're going to move the p to the top to make it a negative sign. Now, one thing we know about this is we can do integration because we're kind of back to, we're in the world of we finished integrals, we finished derivatives, so we can actually just do integration like we're in Calculus 1. And so that means we can just take the antiderivative here, which ends up being x to the negative p plus 1 divided by negative p plus 1. Let's make a quick note. Let's not let p equal to 1. If p equals 1, then we'd be dividing by 0, and this formula wouldn't work at all. But if p equals 1, we'd be using a natural log, and you can follow that along if you like. So we'd be getting this evaluated from, well, I'd like to write an infinity up here, but that's kind of bad form, so I'm going to write the limit as t approaches infinity of that thing. All right, so let's put the t in there, and then we get t to the negative p plus 1 over negative p plus 1 minus, and then I'll put 1 over negative p plus 1. And so this ends up being our limit as t goes to infinity. And what do we know about things? Well, we know that it really all comes down to this term right here. So we know that if I have t to the negative p plus 1, or how about if I just take t to any integer value as t goes to infinity, well, I know it just depends on whether it's 0 or not. So what I get is that if n is less than 0, then I get that this thing equals 0. So let's write that this is 0 if n is less than 0, because then we have fractions and we're getting smaller and smaller and smaller. But it's not equal to 0 if n is bigger than 0, right? So if n is, say, a half or something like that, then if we're taking square roots, that goes on to infinity. So it's infinity if n is bigger than 0. So the real question is just, is it bigger or smaller than 0? And notice I can ask this for this question. So this one converges if negative p plus 1 is bigger than 0 and it diverges, is less than 0. And it diverges if negative p plus 1 is bigger than 0. And let's just look at each of these. Well, that just means that p is bigger than 1, and that just means that p is less than 1. So doing a little bit of math. Okay, so that tells us right now, because we know when this infinite limit converges and diverges, so that tells us instantaneously when this p-series converges and diverges. So this p-series right here converges if p is bigger than 1, and it diverges if p is less than 1. What if p is equal to 1? Let's just write that over here on the side. Well, if p is equal to 1, then we're dealing with the sum as k goes from 1 to infinity of 1 over k, which is the harmonic series that we saw earlier. And we already know that the harmonic series diverges. So that means we put an equal sign here on the diverge side. So if it's equal to 1, it diverges. But it turns out what's interesting about the harmonic series, and the reason why mathematicians are so interested in it, is that it is, in a sense, the largest power that still diverges. So you can take a power of 1 in the denominator, and it's still going to diverge. But once you get any power bigger than 1, it's going to converge. So if I take the sum as k goes from 1 to infinity of 1 over k to the 1.001, that is going to converge. Or importantly, like things that we're a little more familiar with might be something like 1 over k squared is going to converge because you're bigger than 1. However, if I have the sum of 1 over the square root of k, then that's definitely going to diverge because, right, because that one is smaller than 1 because 1/2 power is smaller than 1. So p-series is great. These are like fundamental to the way we think about series. And what we do is when things get more complicated, we often relate them back to p-series in order to make sense of them. And the real question is often this harmonic series. Does it grow faster in the harmonic series or slower than the harmonic series? And that kind of gives you a picture of whether it should converge or diverge. All right. We have 2 tests to end on. The first one is the comparison test. And the comparison test basically just says if we have a bunch of positive values and all of our b values are less than our a values, then one of 2 things, then either one must be the case if the b of k's converge, not converge, diverge. If the b of k's diverge, then so does the a of k's. And then our second result is that if the a of k's converge, then so does the b of k's. Why would this be the case? Well, you can really just kind of see, right? Yeah, so you can really just kind of see. Oh, and by the way, I'm looking at the book and I realize I wrote my A and B backwards to what the book did. So sorry if you're following along in the book, switch your A's and B's and you'll have the same thing that's in the book. But let's just make a quick observation about what's going to happen. And so what we know is once you have these A's of K's and B's of K's, and then we think about the partial series, then let's do S, tell you what, let's put a little B for my partial sum, and then that's always less than or equal to S. I'm just going to put these, this is, by the way, no means standard notation. This is my made-up on-the-spot notation. I'm just trying to talk about the partial sums of the B's versus the partial sums of the A's. And they're slightly different values, but what we know is that the partial sums of the B's are always going to be less than the partial sums of the A's. And so we can see that if these numbers converge, then that means, so if the A's of K's converge, then that means the S in K's converge to some letter L. But then that means that the B K's must be bounded. And that implies, that these partial sums of the BKs must be bounded. And so that means that the partial sums of the B's must converge as well. Okay. Oh, wow. I'm doing an awful job with my notation here. Okay. So in other words, okay. Wow. Okay, sorry about that. So if the A's converge to L, then that means that the B's must be bounded by L, so they must converge also. But now let's look over and let's go, well, what if these partial sums of the B terms diverge? So if those partial sums of the B terms diverge, then that means they're larger than M for any M value. But then that would mean that the partial sums of my A values are also bigger than that M, so that implies that the A's must diverge. So you can just kind of see that what we know about partial sums kind of connects these two things together and makes them work. The last one is limit comparison, and so that is the limit comparison, and that is on the previous example, you might take something like this. 1 over, the sum of 1 over n, let's see, n plus 2, and, n squared plus 2, and so you might compare that to the sum of 1 over n squared, because the n squareds are always smaller. Oh, I put my inequality the wrong way. Right? And so what you see is that these must always be bigger, because if you add 2 to the denominator, major value smaller, and this converges by p-series. And so then this one should also converge by p-series. Okay, so this is how we're kind of do these things and connect these things. But the limit comparison makes a point that, well, it actually doesn't matter if this first series is a little bit smaller. So for example, suppose this, instead of being n squared plus 2, was, say, n squared minus 2. Well, now this inequality is no longer true. So this inequality right here, I would have to block it out, because in fact the one on the left is bigger. But it makes sense that either they should both converge and both diverge, because the values under the denominator are basically the same, especially as n goes to gets gigantic, like a billion. So it makes sense that they would both converge or diverge together. And the answer is correct, and that is what we call the limit comparison test. And so the way we do the limit comparison test is this. We say so first we want our A's and our B's to both be positive sequences for all, and they actually don't want B to equal 0. So A is going to be greater than 0, and our B's are greater than or equal to 0. And this time I'm going to actually try to use the right. Oh, okay. And the reason is because the limit as n goes to infinity of a of k over b of k. That's just because you don't want this limit to not have a bunch of spots where it doesn't exist. Exists. So if you take a limit over the 2 of 1 divided by the other and it exists, then what that means is that the 2 are at a ratio that's consistent with each other. So if it's equal to 3, then that means A is approximately 3 times the size of B as the values of K get really, really large. If the limit is 1, then that means A and K and B and K are basically the same size as N gets really, really large. And then we see a bunch of things. We see, so the first dot is if that A of K over B of K approaches some L limit, right, which is a finite number, then either they both converge or both diverge. Then either AK and BK both converge or both diverge. And let's think about why that should be the case. Well, the reason why that should be the case is if this thing's equal to L, then what you can do is you can do a little bit of arranging. You can say that, well, there exists some n such that after that point, such that if n is greater than or equal to little n, then a sub k minus b sub k is strictly greater than L over 2, and then you can kind of bound these. So that means that a sub k is between L over 2 times b of k and 3L over 2 times b sub k. Oh, okay, right. So there exists some n. I should have been a little bit more careful, where a sub k is between L over 2 and 3L over 2. So all I did was make L a little bit smaller and a little bit bigger. But now you can see that this is the comparison test all over again. So in other words, if the b sub k's diverge, then L over 2 b sub k diverges, and since the a's are bigger, they must diverge. If the b sub k's converge, then 3 over L over 2 b sub k converges, and so the a sub k's must also converge. So you see that because a sub k is bounded between these two terms, which either must both converge or diverge because they're just a constant value difference, then we see that the a sub k's must converge as well with them. The book chooses to skip the proofs when we're in the infinite case, and I'm going to skip them as well. They're actually a lot. They're pretty similar to what we do right here. So if L equals 2, or if they go a sub k, b sub k goes to 0, so maybe I should have up here made sure that L was a positive number. So notice the last theorem dies if it's equal to 0, because your L over 2 is no longer, doesn't have meaning to it. Okay, but if it equals 0, then we get then that means that the b sub k's are growing much faster than the a sub k's, because the b sub k's are kind of going to infinity at a faster rate. So that means the b sub k's are bigger than the a sub k's. So that would mean that bk converges would imply that the a sub k's also converge, because if the so if it's going to 0, that means the b sub k's are growing are bigger numbers, and so dividing by bigger numbers makes your so a sum of numbers that are larger, because right, the idea here is that the b sub k's are bigger than the a sub k's and infinitely bigger than the a sub k's. So that means if they're converging, then the a sub k's are smaller and they must also converge. Okay, finally, if a sub k over b sub k goes to infinity, then we have the opposite case, and that is that here the b sub k's are smaller than the a sub k's. So that means if the b sub k's diverge, then that means the a sub k's must also diverge. All right, because so if it's going to infinity, then that means that the top values are growing at a much larger rate than the smaller values. And doing these proofs really just comes to the point of saying, well, if it's going to 0, then there exists some point where the b sub k's are less than the a sub k's, and then you can finish your proof on out. Okay, I'm going to end this video right here. Our next video, we're going to go through some of the other tests, some of the famous ones like the root and ratio tests and things like that. And the big difference is we're going to involve cases where your terms might not be 0 anymore, or might not be positive anymore. So what happens when we throw some negative values in there? And it makes it all a lot more interesting. All right, I will see you.